In this video, we are going to be finding the area under a curve using integration. The first question, find the area of the finite region bounded by the curve y equals log x, the x-axis, and the lines x equals 2 and x equals 3. So we're going to be integrating a log. We're going to find the integral between 2 and 3 of log x with respect to x. The only way we can integrate log is using integration by parts. So when we're doing integration by parts, the integral of u dv dx with respect to x is equal to uv minus the integral of v du dx with respect to x. So we're going to say it's 1 times log x. We're going to differentiate the log x and integrate the 1. So u is log x, dv dx is 1, which makes du dx 1 over x and v x. So let's put it into our integration by parts. So we want uv, which is x log x, minus the integral of v du dx. V times du dx is 1, so it's the integral of 1 with respect to x, which is just x. And I would plus a constant, but we are going to substitute in 3 and 2 and take them away. So we don't need to worry about the plus c because it would just cancel out. So our area is 3 log 3 minus 3. Take away 2 log 2 minus 2. And so we have 3 log 3 minus 2 log 2. And then we've got negative 3 minus 2. So negative 3 plus 2 is negative 1. So that's the exact area. We will leave it like that. One question for you to try, see if you can give it a go. So find the area of the finite region bounded by the curve y equals 3 over x plus 1, the x-axis, and the lines x equals 2 and x equals 4. That's the integral between 2 and 4 of 3 over x plus 1 with respect to x. When we integrate something to the power of negative 1, or 1 over x, it goes to a log. So we're going to have 3 log x plus 1 as our integral. If the denominator differentiated to give anything other than 1, we would divide by that differentiated, but it's not necessary because it's 1. Between 4 and 2, so substitute in 4, substitute in 2, and take them away. Another question. The diagram shows parts of the curves y equals sine x and y equals sine squared x. The region R is bounded by the 2 curves, so the region we're finding is the one in between the 2 curves. Find the area of that region. So we want the area underneath sine x between 0 and pi, the area underneath sine squared x between 0 and pi, and take them away. So for sine x, we can do that straight away. So the integral of sine x with respect to x between pi and 0. When we integrate sine, we get a negative cos. So it's negative cos x between pi and 0. So it would be negative cos pi minus, so plus cos 0. So we've got negative cos pi plus cos 0, and that is 2. So we've got 2. And for our other area, we want to integrate sine squared x. The only way we can integrate sine squared x is by using our double angle. So it's our cos 2a. So cos 2a is 1 minus 2 sine squared a. So if we want sine squared x, sine squared a by itself, we're going to have, we add it to both sides, we'll get 1 minus, so 2 sine squared x is 1 minus cos 2x, and half both sides. So sine squared x is half of 1 minus cos 2x. So we're going to be integrating half of 1 minus cos 2x between 0 and pi. So let's actually take the half outside so we don't have to worry about that when we're integrating. So we're going to have half of 1 integrates to give x, and then negative cos 2x. So cos integrates to give sine. So it's going to be negative sine 2x, but divide by the bracket differentiated, which is 2. So it's a half of sine 2x. That's integrated. We just need to substitute in pi and 0 and take them away. So substituting in pi, we're getting half of pi minus half of sine 2 pi, and sine 2 pi is 0. So we're just going to get half of pi from this, and then we're taking away sine 0 is also 0. Sine 0 is also 0. So the second one's going to be 0. So let's take away 0. So that is just half of pi. So it's just half of pi. That's all we've got left. So what is the area in between them? So the area underneath our red line is 2. Underneath our blue line is half of pi. So 2 minus half of pi. And one for you to try, see if you can give it a go. So the diagram shows parts of the curves, y equals sine 2x and y equals sine x cos squared x. The region R is bounded by the two curves. Find the region R. So we're finding the area between them. We don't have the label on the x-axis. So where does sine 2x cross the x-axis? So sine x crossed at pi. Sine 2x going to be pi over 2, because you're going to double it, the pi over 2, to get pi, and then that will be the 0. Or it's a squashing the graph in. So when we times inside the bracket, we half the x values. So we're going to integrate both of these. Sine 2x is going to be the easier one to integrate. So between pi over 2 and 0, the integral of sine 2x with respect to x. So sine integrates to give a negative cos, and we divide by the bracket differentiated. So we have minus a half of cos pi, minus a half of cos pi, which is a half, minus a half, so minus a half of cos 0, which is 1. So this is 1. For our other line, sine x cos squared x, we can integrate it by reversing the chain rule. So we can see that cos x differentiated is multiplied by the cos squared x. So our original is going to be something like cos cubed x. So if we differentiated cos cubed x, dy dx would be times by the power, take one off the power, times the bracket differentiated. Cos differentiates to give negative sign. So that would be negative 3 cos squared x. Sine x, we don't want that. So we need to times it by minus a third. So if we times by minus a third to the answer, also times minus a third to what we started with, we get our integral. So it is minus a third cos cubed x. So sine x cos squared x integrates to give minus a third cos cubed x, because minus a third cos cubed x differentiates to give sine x cos squared x. So we want minus a third cos cubed x between, again, pi over 2 and 0, minus 1/3 of cos pi over 2 cubed minus a third of cos 0 cubed is 1/3. So that is just 1/3. So the area between them is 1 minus a third, which is 2/3. So 1 minus 1/3 equals 2/3. So that is our answer, 2/3.